Welcome to a story of cutting-edge technology pushed to its deadly limits, set against the chaos of late World War II. In February of 1945, amidst the ruins of Western Germany, a revolutionary shift in aerial combat was silently unfolding, one that would change everything pilots thought they knew about dogfighting. Could it be that a seemingly simple device, a spring tab, was secretly transforming high-speed fights into unwinnable battles? Why did German pilots suddenly find their sleek fighters almost impossible to control at speeds exceeding 350 miles per hour? What hidden forces, unknown to their engineers, were unleashing chaos in the skies? And how had the British, with their advanced control systems, gained an impossible advantage over the German fighters that once dominated the air? All these questions point to one devastating truth. A technological revolution was quietly erasing the Luftwaffe's edge, turning what should have been a deadly advantage into a fatal vulnerability. In this film, we will trace the hidden origins of this control crisis, unravel the engineering mysteries that confounded even Germany's top scientists, and reveal the shocking ways in which innovation, meant to win battles, ultimately doomed its creators. The most extraordinary secret of high-speed aerial combat is about to be uncovered, and the battle for control in the skies is only just beginning. Now let's dive into the story that changed the face of warfare forever, starting with the first whispers of the control crisis that would haunt the Luftwaffe to the very end. In the waning days of February in the year of 1945, amidst the battered airfields of Western Germany, a tense scene unfolded that would later be etched into the annals of aviation history. It was precisely 4 o'clock in the afternoon when Heinrich Roth, a seasoned pilot of Jagdgeschwader 26, found himself engaged in a perilous aerial duel. Clenching his control stick with desperate resolve, he pushed it hard to the right at an astonishing speed of 400 miles per hour, feeling the burning surge of muscles in his arm under an immense strain. Yet despite his frantic efforts, the stick responded with almost imperceptible movement, merely a centimeter, an indication that his aircraft, a formidable Focke-Wulf FW190, refused to cooperate. In that critical moment, Roth sensed with absolute certainty that he was destined to meet his demise. The trouble was not purely a mechanical failure, but the ominous sign of something unprecedented in modern combat aviation. The aircraft's ailerons, which typically afforded pilots precise control even at high speeds, had become effectively immobilized, frozen at the velocity at which he found himself racing through the skies. Meanwhile, just behind him, a British Hawker Tempest performed an effortless roll into a firing position, its 4 high-velocity 20mm cannons trained directly on his cockpit. The disparity in maneuverability was stark. Roth's FW190 felt almost welded to the airframe, demanding over 60 pounds of force merely to manage a slight deflection of the stick, while the Tempest executed complex maneuvers with apparent ease, as if it was flying at half the speed, in feat that defied everything the engineers of the Luftwaffe understood about high-velocity aeronautical physics. In the span of merely 3 seconds, the situation darkened further. A hail of 20mm shells tore through the air and shattered Roth's canopy, a violent burst of weaponry that marked the end of his aircraft's fight. As his FW190 spiraled downward toward the war-riddled German countryside, it became clear to him that he was yet another casualty of a revolutionary technological shift, one that the brightest minds within the Wehrmacht's engineering corps had scarcely recognized until it was upon them. This revolution was centered around what was known as a spring tab, a seemingly simple device that, in concert with the aircraft's control surfaces, transformed high-speed combat into a deadly game where traditional expectations of maneuverability no longer held true. By the time February of 1945 arrived, this innovative spring tab aileron system had already begun dramatically altering the rules of engagement, often to the detriment of German pilots. Astonishingly, by the end of January alone, 47 pilots of the Luftwaffe had been killed while engaging with the new British fighters armed with these advanced systems. Most of these pilots learned too late that, at speeds exceeding 350 miles per hour, their aircraft would become nearly uncontrollable, unable to respond effectively to their commands or execute essential maneuvers. Instead of a test of skill, high-speed dogfights had transformed into executions, with pilots falling victim to a control system that gave the advantage outright to their opponents. This unsettling vulnerability was no accident, but the consequence of a developing technological disparity rooted deep within the history of aerial combat. The story of Germany's fatal disadvantage extended back much earlier, to the sweltering summer of 1944, when the first reports reached the headquarters of the Luftwaffe about a strange British fighter noticeably defying the physical laws they believed governed high-speed flight. Pilots reported that in engagements at velocities that would threaten their aircraft's structural integrity, the British fighters maintained full aileron control, something they viewed as impossible given the intense aerodynamic pressures faced by German aircraft like the Messerschmitt BF-109 and the Focke-Wulf FW190. At that time, Major Wilhelm Steinmann, who commanded two groups of Jagdgeschwader 26, was quick to dismiss these early accounts as exaggerations or errors on the part of the pilots. He firmly believed that no aircraft, of any design or construction, could sustain effective control forces at speeds hovering around 400 miles per hour without the aid of heavy, cumbersome hydraulic systems, devices that would add to the craft's weight and reduce its flight performance. Steinmann's confidence was bolstered by his extensive combat experience and knowledge of Germany's most advanced fighters. He knew from first-hand familiarity that even the FW190, despite its reputation as one of the most sophisticated warplanes of the era, demanded incredible physical effort from its pilot to perform high-speed maneuvers. Indeed, pilots flying that machine at speeds above 350 miles per hour often needed to exert lateral forces between 45 and 60 miles per hour, 60 pounds on the control stick. Forces that most capable pilots could only sustain for brief moments. The challenges were even more severe in the case of the Messerschmitt BF-109, which faced its own set of aerodynamic and control. The restricted size of the aircraft's cockpit physically hindered pilots from exerting more than approximately 45 pounds of lateral force on the control stick. This limitation rendered full aileron deflection impossible during high-speed maneuvers, especially in combat situations where rapid control inputs are crucial. Such constraints tragically contributed to the deaths of hundreds of German pilots who found themselves helpless and unable to perform effective evasive maneuvers when diving to escape the relentless pursuit of Allied fighters. As pilots attempted to push the aircraft beyond its physical limits, their controls increasingly became stiff and unresponsive, gradually feeling as if they had been carved out of unyielding stone. The underlying technical challenge appeared insurmountable because it was rooted in fundamental principles of aerodynamics and physics. Specifically, as the speed of an aircraft increased, the aerodynamic forces acting upon its control surfaces expanded exponentially. This growth meant that pilots had to exert progressively greater force to move the controls. Eventually, a deadly paradox emerged. The faster the aircraft traveled, the less maneuverable it became. At maximum speeds, fighters transformed into essentially straight-line missiles, incapable of effective turning or rolling, thus significantly impairing their combat effectiveness. In response to this problem, German aerospace engineers experimented with various solutions. One such attempt involved fitting some versions of the Focke-Wulf FW109G with small auxiliary control surfaces called Flettner tabs. These devices helped to reduce the force needed to move the ailerons by providing additional aerodynamic leverage. However, their implementation yielded only marginal improvements and was limited to a relatively small number of aircraft. The majority of Luftwaffe pilots still depended solely on physical strength and meticulous management of their aircraft's speed to preserve control at high velocities, often pushing their limits in the process. The Luftwaffe's top aeronautical specialists, working at facilities located in Augsburg, Dessau, and Recklinghausen, had come to the conclusion that significantly reducing the necessary control forces at high speed, without resorting to hydraulic assistance, was beyond the realm of current technological possibility. They accepted stiff controls as an unavoidable feature of high-performance fighters. This understanding led them to believe that all contemporary advanced fighter aircraft, regardless of nation, shared this fundamental limitation. However, this assumption would prove to be tragically incorrect when the British introduced the Hawker Tempest into active combat in April of 1945-1944. The Tempest incorporated revolutionary technology that German engineers had not previously considered, an innovation that would dramatically alter the understanding of high-speed aerial maneuvering. Central to this advancement was the implementation of a spring-tab aileron system designed to automatically compensate for aerodynamic forces as speed increased. This system allowed British pilots to retain high levels of control sensitivity even at the blisteringly high velocities where German pilots struggled to move their sticks at all. The mechanism itself was deceptively simple. It consisted of a small auxiliary control surface, referred to as a spring tab, mounted on the trailing edge of each aileron. This tiny tab was mechanically linked to the primary control system via a calibrated spring that compressed under aerodynamic loads during high-speed flight. As the aircraft accelerated and the aerodynamic forces grew stronger, this compressed spring caused the tab to deflect in the opposite direction of the aileron's movement. This deflection generated an aerodynamic force that effectively augmented the pilot's input, easing the movement of the main control surface. As the aircraft's speed increased and aerodynamic pressures intensified, the spring within the system compressed more, causing the spring tab to deflect further and provide greater aerodynamic assistance. This automatic adjustment meant that the system could almost perfectly compensate for the control heaviness caused by high velocity, maintaining a nearly consistent amount of force required by the pilot to roll, bank, or yaw the aircraft across the entire speed spectrum. One of the notable figures involved in evaluating this advanced system was British test pilot Eric Brown. In the course of assessing captured German aircraft, Brown observed during his initial flights in the Tempest that the spring tab system made the aircraft feel startlingly responsive at high speeds, so much so that it seemed almost unnaturally nimble. The Tempest retained high roll rates at velocities that, for German pilots, would have been impossible to manage with their traditional stiff controls. The presence of the spring tab mechanism fundamentally changed the game, providing pilots with a level of control that had previously been elusive at such speeds, thus giving the British a significant tactical advantage during aerial combat. Imagine experiencing a kind of superhuman strength that radically redefines the way a pilot controls a fighter aircraft, especially during high-speed maneuvers. This sensation, akin to what one might describe as the feeling of power steering before the advent of modern systems, allowed pilots to execute incredibly precise and effortless control inputs. What made this sensation particularly remarkable was the aircraft's ability to remain highly responsive, even at velocities where conventional fighters typically struggled to be manageable. At speeds where other aircraft became almost uncontrollable due to excessive control forces, this fighter responded smoothly and effortlessly. This groundbreaking system had been meticulously developed through comprehensive wind tunnel testing conducted at the Royal Aircraft Establishment in Farnborough. Engineers from Hawker collaborated closely with specialists at their Langley facility, dedicating countless months to perfecting the balance of springs and the geometry of control tabs. The goal was clear: to reduce the forces needed to move the control surfaces to an optimal level where pilots could command high speeds with ease. Crucially, they had to carefully avoid introducing aeroelastic problems, such as flutter, which could rip the aircraft apart when flying at peak velocities, a challenge that required a delicate balance of materials science and aerodynamic tuning. German pilots encountered this technological marvel for the first time during the Normandy campaign, and their impressions were stark. As the battle intensified, the Tempest began appearing increasingly frequently over the battlefield, prompting countless combat reports. These reports vividly described German fighters performing seemingly impossible maneuvers, aggressive rolls and tight turns, at dive speeds where enemy aircraft became practically unmanageable. The Germans found that their fighters, which normally struggled with control forces at high speed, became immobilized, while the Tempest maintained maneuverability that defied their understanding of aerodynamics and control force limitations. One particular encounter that highlighted this advantage involved Joseph Priller, a highly experienced fighter ace from the Luftwaffe with over 100 aerial victories. During a fierce confrontation over Belgium in September of one year, Priller faced a Tempest at high velocity. Later, he recounted how his Focke-Wulf FW190 seemed to transform into a thing made of concrete at about 400 miles per hour, completely unresponsive to the lateral stick forces he was accustomed to applying. Meanwhile, the British Tempest darted around him with agility reminiscent of an aircraft at stall speed, executing a perfect barrel roll that for a German pilot of his caliber would have been physically impossible to perform under similar conditions. Such encounters accumulated in the combat reports throughout the autumn, casting a disturbing shadow over the Luftwaffe. They painted a clear picture. Their aircraft, once trusted for their robustness and maneuverability, were now outmatched aerodynamically. Pilots repeatedly described the feeling of being outmaneuvered at speeds approaching or surpassing their aircraft's typical control limits, the Germans' fighters feeling as if they had become rigid flying bricks. The situation was particularly dire for pilots flying the BF109. Its notoriously narrow cockpit made it physically difficult to apply the lateral forces necessary for aggressive, high-speed maneuvers. Faced with this limitation, many would prematurely enter high-speed dives in an attempt to escape dangerous situations. Unfortunately for them, these dives often left them in straight-line trajectories, while Tempests, thanks to their advanced control system, followed their descent effortlessly, maintaining superior maneuverability and control. This advantage often turned what should have been a simple escape into a trap where the Germans' aircraft remained stiff and unresponsive, unable to match the agility of the Tempest. By November of that same year, as reports continued to flow in with alarming frequency and detail, the leadership of the Luftwaffe recognized the urgent need to understand this newfound technological edge. General Dirge Jagdflieger, along with Anton Galland, issued an order for a rigorous technical investigation into the mysterious capabilities of the Tempest. They assembled teams from the engineering firms Meshmet and Fala-Wolf, tasking these experts with analyzing combat footage and examining wrecked aircraft remains. Their mission was to uncover the secret behind the Tempest's extraordinary control at high speeds, a secret that allowed British pilots to dominate in maneuverability even under extreme conditions where German fighters felt sluggish and unresponsive. Initially, the engineers focused their efforts on common theories. Their suspicions pointed toward advanced hydraulic systems or innovative aerodynamic designs, perhaps some sort of revolutionary control surface mechanism that could amplify control inputs. However, they overlooked a more straightforward explanation. The crucial element was actually a relatively simple mechanical device, an ordinary trim tab, that had been visible on crashed aircraft. Until that point, they had dismissed this as just another component of the aircraft's control system, not recognizing how vital its role was in facilitating such exceptional high-speed maneuverability. The breakthrough finally occurred in December of that year, when Luftwaffe technical intelligence officers at Reclan carefully examined a relatively intact crashed aircraft. Their detailed inspection revealed that what they thought was ordinary trim tab technology was actually something far more sophisticated than previously assumed. This realization marked a turning point, as they understood that the incredible agility. During a fierce aerial engagement, a formidable Tempest was forcefully brought down near the Rain airfield, marking a significant and alarming event in the ongoing conflict. This incident prompted an urgent and meticulous investigation into the airframe and its control systems, leading to a groundbreaking discovery that would forever alter the understanding of aircraft maneuverability at high velocities. Engineers, under the leadership of the esteemed Dr. Friedrich Zimmermann from the Deutsche Versuchsanstalt für Luftfahrt, scrutinized the wreckage in an effort to uncover the secrets behind the aircraft's exceptional performance, particularly focusing on the control mechanisms that had apparently enabled the pilot to maintain formidable agility, even under extreme conditions. Initially, the examination revealed a startling anomaly in the aircraft's control system, puzzling the engineers who had expected the usual mechanical linkages. As they dissected the components, their attention was drawn to a surprisingly simple yet ingenious mechanical device known as the spring tab system, a mechanism designed to alleviate control forces and make aircraft handling more manageable at high speeds. The technicians conducting rapid calculations and tests quickly realized something extraordinary. This minor, seemingly modest addition was capable of reducing the pilot's control effort by a staggering 70% when operating at maximum velocities, dramatically improving responsiveness and safety during daring maneuvers. Dr. Zimmermann's comprehensive report to the Air Ministry conveyed this discovery with unmistakable clarity and concern. It emphasized that the enemy had seemingly engineered a control system upgrade far beyond what was conventionally anticipated, equipping their most recent fighters with a technological advantage that challenged all previous assumptions. The report noted that this innovative system enabled their pilots to retain full combat maneuverability at speeds where otherwise the aircraft would become nearly uncontrollable, a stark realization that the Germans desperately needed to address if they wished to compete effectively. The report further explained that implementing similar advancements into existing German fighters would not be a trivial task. It would demand extensive redesigns of aircraft frameworks and control linkages, accompanied by lengthy periods of flight testing and qualification, a process that could unwind over months or even stretch into many years, delaying any quick adoption of such technology. Confronted with this stark reality, a crisis meeting was convened at the Luftwaffe headquarters, where the top brass gathered to reassess their strategic position in the escalating air war. During this tense gathering, General Pilot Adolf Galland openly confronted Hermann Göring about the emergent technological disparity, warning him that the British fighters had gained a critical, perhaps decisive, advantage through the incorporation of this control system. The implications were grave. This advantage could nullify traditional tactics and undermine the Luftwaffe's fighting edge, significantly complicating their efforts to maintain air superiority. This revelation intensified existing tensions within the leadership hierarchy, highlighting the urgent need for rapid innovation or adaptation to counter these airborne advancements. Meanwhile, across the Pacific, Japan and Germany's Axis allies faced a similar shocking revelation. The Imperial Japanese Army Air Force was encountering American fighters armed with equally sophisticated control systems. Their pilots discovered that these high-performance American aircraft, namely the P-51 Mustangs and P-47 Thunderbolts, retained a high degree of control and responsiveness at speeds where Japanese fighters, such as the Mitsubishi Zero, experienced severe control heaviness. Above 300 miles per hour engaging in aggressive maneuvers became nearly impossible as the control forces demanded enormous physical effort, rendering swift, precise combat responses and evasive tactics impractical and increasingly dangerous. Japanese ace Makoto Ogawa, renowned for his exceptional prowess and credited with downing 7 B-29 Superfortresses, reflected on these challenges in his post-war memoirs. He vividly described high-speed dogfights against American fighters as akin to fighting with one hand tied behind your back, emphasizing how the controls on Japanese aircraft grew stiff and unmanageable at elevated speeds. Despite attempts to improve the situation, including developing interconnected aileron flap systems designed to assist with control heaviness, these modifications never approached the simplicity and effectiveness of the British spring tab system or its Japanese equivalents. As a result, they remained vulnerable to the same high-speed control issues that plagued their German and Italian allies. The Italians, for their part, faced analogous problems with their aircraft, such as the Macchi C-202 Falore and the C-205 Veltro. Their pilots, including a notable ace like squadron leader Franco Lucini, had repeatedly complained about the increasingly wooden sensation of their fighters during high-velocity pursuits. Such stiffness in control made it physically exhausting and often tactical impossible to perform sudden turns or evasive maneuvers at speeds exceeding 300 miles per hour, a critical handicap in high-stakes combat situations. As the war progressed into the year of 4043, Hawker Aircraft commenced the production of Tempest, fitted with the revolutionary spring tab ailerons at their Langley facility. The adoption of this highly effective system marked a significant boost to aircraft maneuverability. The technology was gradually integrated into new aircraft models, making high-speed actions more responsive and easier for pilots to execute, thus helping the Allied forces to regain certain tactical advantages lost earlier. In the effectiveness of the innovative spring tab control system was not achieved overnight. Rather, it was the result of thorough and meticulous flight testing aimed at pinpointing the ideal spring tension and tab dimensions. This extensive testing effort revealed settings that maximize control and maneuverability without compromising the structural integrity of the aircraft. The initial production run, which consisted of 100 of the Tempest I series of airframe fighters, was equipped with this spring tab system from the very beginning. However, during the latter part of 1944, some of these aircraft were temporarily taken out of active combat duties. The reason for this was the realization that the remarkable increase in agility and responsiveness made possible by the spring tab could, under certain conditions, impose excessive stresses on the airframe. When pilots responded to high control forces by executing maximum control inputs at speeds near the aircraft's limit, it sometimes led to structural overloads. Consequently, this prompted the need for minor yet vital reinforcements to the airframe's structural components and highlighted the importance of specialized pilot training, emphasizing the new handling characteristics introduced by the spring tab system. Sidney Cam, who served as the chief designer at Hawker, was among the earliest to understand the potential limitations posed by high-speed control forces. Based on his earlier experience with the Typhoon, which was known for its exceptionally heavy controls that could fatigue pilots during prolonged combat operations, Cam recognized that overcoming control force issues was essential to fully realizing the Tempest capabilities. The spring tab concept arose from collaborative efforts with aerodynamic specialists at the Royal Aircraft Establishment, who had been investigating various methods to lighten control forces without resorting to the cumbersome and often unreliable hydraulic systems. In this context, the spring tab emerged as a solution, offering an optimal balance of responsiveness, simplicity, and dependability, all while maintaining a manageable weight profile. The process of manufacturing the spring tab-equipped ailerons was an exemplar of precision engineering. Each spring mechanism required careful calibration, with every aircraft individually tested to ensure that the tabs responded correctly across a broad spectrum of speeds. Such demanding quality control standards posed a significant challenge, especially considering the deteriorating industrial conditions in Germany by 1944, which hampered their ability to produce comparable high-precision components. At Hawker's Langley facility, the assembly work was primarily carried out by skilled workers, many of whom were women who had stepped into roles previously held by men called into military service. These workers meticulously assembled the spring tab mechanisms, measuring tolerances in just thousandths of an inch. They understood that their rigorous attention to detail was directly linked to pilot safety during high-speed combat, where a single small mechanical flaw could be the difference between life and death at speeds approaching 400 miles per hour. The combat effectiveness of the spring tab innovation was vividly demonstrated during the critical months from December of 1944 through February of the following year. During this period, Tempest squadrons equipped with the system inflicted heavy losses on German aircraft, claiming a total of 239 enemy fighters destroyed with only 20 of their own aircraft lost, a staggering kill ratio of approximately 7-1. This statistic highlighted not merely the skill of the pilots, but crucially, the tangible advantage gained by maintaining superior control at speeds where enemy fighters typically became nearly helpless, unable to escape or effectively respond. One of the foremost pilots to take full advantage of this technological edge was squadron leader David Fairbanks, who was recognized as the highest-scoring Tempest ace of the war. Fairbanks described numerous encounters where German fighters attempted daring escapes by diving at high velocities. Nevertheless, these aircraft, now routed into high-speed dives, often found themselves trapped in straight-line flight with no option to maneuver effectively. Meanwhile, Fairbanks and his squadron could still execute aggressive, controlled maneuvers that kept them in optimal firing positions. Consequently, what should have been successful escape attempts for the enemy frequently turned into disastrous engagements, giving rise to what pilots fondly referred to as turkey shoots. The psychological impact on Luftwaffe pilots was profound. They quickly became aware that the Tempest control system gave their adversaries a distinct and insurmountable advantage at high speeds. No amount of piloting skill, courage, or daring could negate the fundamental mechanical superiority provided by the spring tab system. This realization, coupled with overwhelming losses against the Tempests, eroded confidence among German fighter pilots and created a crisis within their ranks. The deficiency in high-speed handling capabilities, something that was once less apparent, became glaringly obvious, generating a pervasive sense of helplessness. It was this mounting sense of vulnerability among Luftwaffe crews that spelled trouble not only on individual missions, but also throughout their fighter units, undermining morale and fueling a strategic advantage for the Allies, one that was fundamentally rooted in the elegant simplicity and high precision of the spring tab control mechanism. Bulligan of Jagasheer II, a seasoned veteran who had participated in over 100 combat missions, once penned a heartfelt letter to his wife in January of the year 1945. In it, he expressed a profound sense of frustration, remarking that their forces were still fighting with weapons designed and perfected in a bygone era, while their enemies had already harnessed technologies of the future. This sentiment vividly illustrated the helplessness he felt as he watched enemy Tempest aircraft maneuver with remarkable agility and speed, far beyond anything his own FW190 fighters could achieve. To Bulligan, it seemed as if his aircraft had suddenly become as cumbersome and sluggish as a loaded bomber when compared to the sleek, cutting-edge Tempests executing sharp turns and high-speed dashes effortlessly through the sky. The German aviation industry faced monumental challenges in trying to rapidly develop and implement new control technology to counter the superior maneuverability of the Allied fighters. Their efforts were hampered by a constellation of insurmountable obstacles. Severe shortages of critical materials made manufacturing difficult, while strategic bombing campaigns dispersed factories across the German homeland, breaking up production lines and depriving them of the centralized efficiency needed for swift development. At the same time, many experienced engineers, vital for the design and testing processes, had been lost, either to military drafts or captured by Allied forces, further delaying progress. As a result, designing, testing, and deploying a comprehensive and reliable control augmentation system in time for the spring deployment became virtually impossible, cloaked in the fog of war and material shortages. In a limited attempt to improve control response, a handful of FW190D13 models were fitted with hydraulic aileron boost systems, an urgent stopgap measure. However, only a few such aircraft emerged before the war concluded. This modification was, at best, a hurried patch. It added significant weight and complexity to the aircraft's already intricate systems, thereby diminishing overall performance under many flight conditions. As such, this technological patchwork served as a poorly integrated substitute for the more elegant and simple mechanical solution known as spring tab, a refinement that had promised both improved maneuverability and ease of control. Meanwhile, the Luftwaffe's fighter force was already stretched thin, severely hampered by fuel shortages, a lack of well-trained pilots, and a dwindling numerical advantage. The combat disadvantage created by their inability to utilize advanced control systems only compounded their difficulties. German pilots, acutely aware of their craft's limitations, increasingly avoided engaging in high-speed dogfights where they faced the deadly precision of Allied aircraft, like the Tempest. Instead, they resorted to tactics such as the daring attack on Allied airfields on January 1, 1945, the operation known as Boden-Platte, where a massive surprise strike was launched. This offensive aimed primarily at attacking vulnerable ground targets or destroying enemy fighters while they were unsafe on the ground, as aerial combat at high speeds was becoming a near-suicide mission for German pilots facing Tempests with notably superior control and agility. The advantages of the Tempest's innovative control system, the spring tab, extended beyond mere agility in battle. Tempest pilots were able to adopt aggressive pursuit tactics that would have been physically taxing or impossible for pilots flying older, conventional fighters. The spring tab technology significantly reduced the amount of force needed to manipulate the aircraft's control surfaces, allowing pilots to sustain longer sorties without tiring prematurely. This reduced fatigue meant they could maintain peak combat performance over extended periods, an invaluable asset in the demanding sky battles of late-war Europe. Flight Lieutenant Pierre Klusterman of the 274 Squadron recounted how the transition from flying standard Spitfires to Tempest transformed his combat endurance. He observed that he was able to fly twice as long before experiencing the debilitating arm and shoulder fatigue that had previously limited his effectiveness during prolonged dogfights. Thanks to the spring tab's design, control inputs felt almost effortless, akin to moving through the air rather than battling against it at high speed, improving decision-making, response time, and the ability to sustain aggressive tactics relentlessly. Post-war technical analyses conducted in the United States, where captured German fighters underwent extensive testing and scrutiny, confirmed the severity of the control issues that had plagued the Luftwaffe fighters. American test pilots examining the Allied fighters reported astonishment that German pilots had managed any level of success at high speeds, given the physical limitations imposed by their aircraft's control mechanisms. The detailed evaluation revealed that although the FW190 performed admirably at low and medium speeds, it became perilously difficult to control above approximately 400 miles per hour. At such high velocities, the aircraft's control forces increased dramatically, requiring pilots to exert substantial physical effort, a factor that greatly constrained their combat capabilities and responses during high-speed engagements. In essence, while the FW190 was celebrated for its excellent handling at lower speeds, making it a formidable fighter in certain combat scenarios, the need for technological improvement at high velocities remained painfully evident. The control forces at these speeds strained even the most hardened pilots, exposing vulnerabilities at enemy aircraft with their advanced maneuver. The challenges faced by combat pilots in controlling their aircraft at high speeds were a persistent and daunting obstacle throughout the war. For instance, the German Focke-Wulf FW190G variant, widely regarded as a formidable fighter, was hampered by a particularly narrow cockpit design. This seemingly minor issue had profound implications. It physically limited most pilots from exerting enough lateral force on the control stick to achieve full aileron deflection during rapid maneuvers. In essence, this meant that no matter how skilled or determined a pilot was, the aircraft's design effectively restricted their ability to perform swift and precise turns when it mattered most, especially in the heat of combat. Contrasting the FW190G with other aircraft, Captain Eric Brown of the Royal Navy, who had extensively tested both German and British fighters, offered one of the most scathing and insightful evaluations of the German design. Brown pointed out that the lack of spring tabs or similar control augmentations on the FW190 had serious repercussions. At maximum speeds, the aircraft's control surfaces essentially became ineffective, making it feel as though the pilot had no ailerons at all. This deficiency rendered rapid lateral maneuvering incredibly difficult, if not impossible. In comparison, the British Hawker Tempest maintained a consistent level of responsiveness across its entire speed range, an attribute Brown described vividly. He explained that controllability at high speed in the Tempest was akin to the difference between wielding a well-designed weapon and swinging a heavy club. The aircraft's readily accessible control forces allowed pilots to execute maneuvers confidently, regardless of how fast they were flying. However, Brown's critique of the FW190G was even more pointed. He vividly highlighted how that aircraft's combination of a narrow cockpit, clogged with its controls, and heavy control forces created a veritable death trap at high speeds. In such moments, pilots faced a harsh reality. They simply could not generate enough physical lateral force to effectively maneuver, regardless of their skill level or experience. This limitation posed a severe danger in high-stakes combat situations, where milliseconds and precise control could determine survival. Interestingly, after Italy surrendered during the war, its Regia Aeronautica pilots evaluated, captured Allied aircraft with a sense of wonder at the advanced control systems imbued in certain fighters. Test pilots reported that flying a captured Hawker Tempest after having flown Italian Macchi fighters was akin to switching from commanding a truck to flying a racetrack-ready racing car, an analogy emphasizing ease of control at high speeds. Particularly striking was the fact that Italian pilots noticed how much effort was required to control their fighters as speeds increased to the maximum, which contrasted sharply with the comparatively effortless control of the Tempest at similar velocities. Major Adriano Visconti, one of Italy's most tenacious and successful fighter aces, had the rare opportunity in early 1945 to fly a captured Tempest. He observed that the presence of spring tabs, the simple yet effective aerodynamic control aids, would have profoundly changed the game for Italian aircraft designs. Visconti believed that if Italian fighters possessed similar control augmentation technology, it might have shifted the strategic balance of aerial combat over the Mediterranean, giving Italian pilots a far greater fighting chance against Allied aircraft. Across the Pacific and in Japan, despite their reputation for innovative aircraft design, the Japanese military never fully addressed the fundamental problems associated with high-speed control forces. Their emphasis on constructing lightweight fighters optimized for agility at low speeds often came at the expense of high-speed maneuverability. As a result, Japanese fighters became essentially helpless in high-speed dogfights against American aircraft equipped with advanced control augmentation systems. Interrogations conducted after the war revealed that many Japanese pilots remained baffled about why American fighters could outmaneuver them at high velocities. Rather than understanding that the technological advantage lay in systems such as spring tabs and other control force-reducing mechanisms, they attributed their losses to inferior pilot training or inexplicable, mysterious technology. This misattribution masked the critical role that control systems played in maintaining aircraft maneuverability across the entire speed spectrum. Meanwhile, Soviet engineers, in their post-war efforts to catch up with Western advancements, studied captured German aircraft with great interest. They also obtained some British technical intelligence through Lend-Lease agreements. These insights quickly underscored the importance of integrating control force reduction solutions into Soviet fighter design. Early attempts, however, were hampered by difficulties in replicating the British elegance and efficacy of the spring tab system. It took considerable effort and innovation to develop control enhancement methods suitable for Soviet manufacturing and engineering principles. The Soviet Design Bureau, led by Alexander Yakovlev himself, was especially attentive to this problem. Recognizing the apparent simplicity of the spring tab as a solution to a highly complex control issue, Yakovlev noted that the Western approach had been correct, that previous Soviet efforts had been approaching the challenge from entirely the wrong angle. By studying this hardware, Soviet engineers evolved new control systems that ultimately enhanced the maneuverability of later fighters. These improvements played following the devastating conflicts of the Second World War. The revival of the French aviation sector marked a remarkable period of resilience and ingenuity. Thanks to its access to cutting-edge German aerospace technology acquired during and after the war, as well as innovations utilized by the Allies, the French engineers embarked on extensive and meticulous research into aircraft control systems. Among the many breakthroughs studied, one element stood out as particularly revolutionary, yet historically underappreciated: the spring tab control system. A dedicated team of engineers at SNK-CMA, the National Service of Aeronautical Mechanics, concluded that this small but vital component represented a technological leap of significance. It provided a distinct advantage in aerial combat, an advantage so powerful that it influenced the outcome of countless dogfights during the war years, even though many pilots and commanders failed to comprehend the true nature of its influence. At the heart of this technological renaissance was Marcel Dassault, an innovative engineer whose vision would later shape one of Europe's leading fighter aircraft manufacturers. From an early stage, Dassault insisted that future fighter designs incorporate advanced control help devices, such as refined control aids, which would enhance maneuverability and pilot endurance. His conviction was strengthened by witnessing the tragic consequences of control force limitations on Axis fighters, a factor that often resulted in costly losses without the crew ever understanding the technological shortcoming. These limitations hampered pilots' ability to execute precise and rapid maneuvers as combat situations intensified. The factory data from this period paints a stark and grim picture of the evolving aerial battlefield. By the conclusion of the war, British Hawker Aircraft Factory produced an astonishing 1,720,000 Tempest fighters, an incredible number that dwarfed the production figures of their German counterparts. Most of these Tempests were equipped with the innovative spring tab ailerons, a feature that vastly enhanced control response. In contrast, German efforts to adapt and retrofit similar systems to their existing fighters resulted in only a handful of aircraft modified with such technology before the collapse of the Reich. The disparity in production capacity and technological application underscored the strategic and technological gap between the Allies and Germany. By early 1945, the Langley factory alone was producing up to 15 Tempests weekly, each one a flying testament to the technological edge that could dominate high-speed aerial combat. This rapid and prolific manufacturing meant that each new Tempest added to the Allied air superiority was a formidable threat to German fighters, whose dwindling numbers could barely keep pace. While German factories struggled under relentless bombing campaigns and scarcity of essential resources, the human toll of this technological and industrial disparity was staggering. German fighter pilot losses soared to unsustainable levels by early 1945. Such losses forced the Luftwaffe to cut back on offensive operations, relegating many fighters to defensive or secondary roles, and increasingly avoiding combat altogether, except under the most advantageous conditions. This retreat from the chaos of frontal engagement effectively handed dominance in the skies to the Allies. The toll was not only measured in aircraft and personnel, but also in the devastating psychological impact on the German fighter pilots. Especially notable was the situation in January of 1945, when the Luftwaffe suffered the loss of 47 experienced pilots in a single month fighting against the Tempest. These losses were equivalent to an entire fighter group, decimating the operational effectiveness and morale of German units. Replacements were desperately needed, but the manufacturing and training pipelines had dramatically broken down. Germany's once effective pilot training programs had faltered, resulting in fresh pilots entering combat with minimal flight hours and inadequately prepared for the turbulence of high-speed dogfights. The loss of seasoned pilots compounded the crisis, as inexperienced replacements lacked the skill to handle modern fighter aircraft effectively. The psychological effects of this technological advantage, embodied in the innovative spring tab system, should not be underestimated. As reports circulated among LUFTWAFFE units about the Tempest's seemingly supernatural agility and control finesse, these tales fostered fear and a sense of foreboding among the German pilots. The enhanced maneuverability granted by the spring tab system appeared almost miraculous, inspiring both admiration and anxiety, which in turn diminished combat confidence even before a single engagement. Much of the German fighters' lost effectiveness stemmed from this collective apprehension, as pilots hesitated or fought defensively, knowing that engaging a Tempest at high speed was often a one-way ride to disaster. This growing tactical disadvantage was epitomized by tales from Wing Commander Roland Beaumont, the veteran leader of the first Tempest wing to engage in combat. Reflecting on those early battles, he remarked that the spring tab control system had provided the Allies with a crucial edge, an unseen advantage that their adversaries never anticipated. It transformed an already capable aircraft into a dominant force in aerial combat through a seemingly modest mechanical innovation. He remembered that many of his pilots never fully appreciated the extent of the advantage they now possessed. They often attributed their success solely to superior tactics or training, unaware that the aircraft itself boasted control characteristics unattainable by the German fighters. This near unbeatable agility, especially at high speeds, was the advantages of the spring tab control system, particularly in terms of maintenance and reliability, overshadowed the more complicated hydraulic alternatives that were available. This mechanical system was remarkably durable, often requiring only minimal upkeep and rarely experiencing malfunctions. Unlike hydraulic systems, which often added considerable weight, increased complexity, and numerous potential points of failure, the spring tab design presented a streamlined solution that could be trusted during vital combat moments. Ground crews operating from forward airfields could easily maintain and fine-tune these spring tab systems using nothing more than basic hand tools, a significant advantage when compared to hydraulic controls that demanded specialized equipment and expertise. As wartime logistics grew increasingly strained, it became clear that such complexities would be impractical and difficult for the declining supply networks of the Luftwaffe to sustain. Furthermore, the aerodynamic profile of the spring tab solution deserves particular praise due to its efficiency. The small metal tabs, carefully designed, provided substantial control benefits while adding only a negligible amount of drag to the aircraft, a critical factor for fighter planes that thrived on maximum speed and maneuverability. Unlike larger balance tabs or alternative mechanical aids that could significantly hamper performance by increasing aerodynamic resistance, these tiny control surfaces offered an optimal compromise. During high-speed flight, even small differences in drag could translate into crucial speed losses, which in combat could mean the difference between victory and defeat. Extensive wind tunnel testing at Farnborough played a crucial role in perfecting the precise size and positioning of these tabs, Engineers optimized the setup to achieve the greatest possible reduction in control force requirements while introducing minimal drag. This meticulous process resulted in a level of aerodynamic refinement that German engineers, faced with the pressures of wartime production and limited resources, could only aspire to. Their attempts, often constrained by the chaos of war, fell short of the finely tuned efficiencies that British engineers attained. Beyond direct combat benefits, the innovative spring tab system also dramatically influenced pilot training and operational psychology. Because the control surface required less physical effort to maneuver, pilots could fly effectively without exhaustive physical conditioning. This meant that older pilots or those of smaller stature could maintain combat readiness, an invaluable advantage given the increasing scarcity of seasoned personnel as the war dragged on. The reduced physical demands made their training less physically taxing, helped lower pilot discard rates, and expanded the pool of qualified combat pilots. In contrast, the Luftwaffe aircraft, struggling with pilots who lacked the raw physical strength to control their aircraft at extreme speeds, faced greater challenges in pilot retention and performance. The British approach to aircraft control exemplified pragmatic engineering, resolving a critical operational problem through simple, robust solutions, rather than resorting to overly complicated over-engineering. The decision to utilize springs and tiny metal tabs was a deliberate design philosophy rooted in reliability, ease of manufacturing, and operational effectiveness. This starkly contrasted with the German tendency to develop highly sophisticated systems, such as hydraulic controls and variable geometry wings, complexity often accompanied by greater susceptibility to failure and more demanding production requirements. While German engineers invested heavily in the development of hydraulic systems, intricate control linkages, and technologically advanced wing configurations, British engineers prioritized straightforward, functional solutions. The resulting performance disparity was reflective of deeper philosophical differences between the two sides, differences that, in this case, had tangible implications on wartime effectiveness. Post-war evaluations, including a comprehensive analysis by the United States Strategic Bombing Survey, underscored the importance of such technological innovations. They highlighted how advances like the spring tab control surfaces had cumulative effects that extended well beyond immediate combat scenarios. By easing pilot workload, empowering less physically capable pilots, and ensuring more consistent aircraft control, these systems indirectly contributed to the morale decline of the German forces. They recognized that as the war progressed, the Germans found themselves falling behind in key technological domains, areas in which British and Allied innovations had provided a decisive edge. The survey detailed how German pilots and engineers had underestimated the technological gap that was quietly widening, assuming a parity with the Allies that was increasingly untrue. Discoveries and incremental improvements, such as the spring tab control system, proved that technological superiority often depended not only on the complexity of engineering, but also on practical, reliable design choices rooted in common engineering principles. These insights highlighted the fundamental divergence in approach: Britain's emphasis on practicality and streamlined solutions versus Germany's tendency toward intricate complexity. Such distinctions played an understated but significant role in shaping the outcome of the conflict, proving that elegant simplicity could sometimes overshadow technological sophistication. In summary, the introduction of the spring tab control mechanism marked a pivotal evolution in wartime aircraft engineering, demonstrating that effective control could be achieved with minimal weight, reduced maintenance, and increased reliability. The resulting aerodynamic efficiency, operational simplicity, and pilot-friendly characteristics reinforced the superiority of this approach compared to more elaborate German innovations. The system's development at Farnborough, driven by meticulous testing and engineering pragmatism, ultimately proved that smart, straightforward solutions could resolve critical technical challenges better than complex, resource-demanding alternatives. These technological victories accumulated over the course of the war, subtly shifting the balance of aerial combat and contributing significantly to the Allied advantage. An enduring testament to the development of the spring tab system represented a significant breakthrough in aircraft control technology, and its impact on aerial combat during World War II proved to be especially profound, delivering blows to the confidence in the well-regarded German engineering prowess of that era. The effectiveness of this seemingly simple innovation in aircraft control mechanisms quickly became evident, revealing that many of the earlier assumptions about the superiority of German-designed aircraft were increasingly becoming questionable. The influence of the spring tab system extended well beyond the conflicts of this war, with various versions of the technology appearing in civilian and military aircraft long after the war had ended. This enduring legacy is a clear testament to the fundamental robustness and ingenuity of the concept that engineers at Hawker had developed under the intense pressures of wartime necessity. In fact, modern fly-by-wire systems, which incorporate artificial feel and automatic control force adjustments, can be traced directly through a lineage of technological thought back to these rudimentary yet revolutionary spring tabs. Those initial devices provided Tempest pilots with a critical advantage in aerial maneuverability that could sometimes determine the outcome of dogfights, demonstrating how wartime innovation could leave a lasting imprint on the trajectory of aviation technology as a whole. The story of the spring tab also exemplifies the dangers inherent in certain technological assumptions and highlights the vital importance of ongoing innovation and adaptation. For instance, German engineers of the era often believed that controlling high-speed aircraft was only feasible through the use of complex hydraulic systems, which they viewed as the only solution to the challenges posed by rapid maneuvers. This conviction blinded them to simpler, more elegant solutions, a short-sightedness that their enemies had already exploited. Such a technological blind spot ultimately proved costly. It resulted in the deaths of hundreds of German pilots and significantly handicapped the Luftwaffe's ability to contest Allied air superiority during the final months of the war. In this context, the criticality of a single overlooked invention becomes starkly clear. An innovation as straightforward as the spring tab could have strategic implications. Personal accounts from German pilots who narrowly escaped encounters with Tempest offer vivid, visceral testimonials to the terror of helplessness at high speeds. They describe moments when aircraft became unresponsive at critical junctures, leaving pilots unable to maneuver effectively while the enemy fighter maintained complete control. These instances transformed what should have been a high-speed dive into an advantage into a deadly trap, often with fatal consequences. One notable survivor was Major Wilhelm Hoffmann, who was shot down by a Tempest in February of 1945. His recounting of the experience vividly captures the sensation of paralysis and helplessness, comparing it to being immobilized while someone violently beat him. During this encounter, his Messerschmitt BF109G6 lost all responsiveness at around 400 miles per hour, while the Tempest behind him appeared to move with a grace and agility that resembled a dancer performing a flawless routine. This terrifying vignette highlights how control limitations could turn a seemingly superior aircraft into a death trap in combat. Exploring the industrial archaeology of the Hawker Langley factory, a site largely destroyed by post-war development, reveals additional evidence of the meticulous craftsmanship involved in producing these control components. Archival records and physical remains show a level of precision manufacturing required for assembling spring tabs, which involved the use of specialized jigs and fixtures designed specifically to ensure consistent spring forces and precise alignment across hundreds of aircraft. Memoirs from workers involved in the production process describe a rigorous emphasis on quality control, underscoring how even seemingly minor variations could prove decisive in combat situations. Management stressed to workers that a variation as small as a tenth of an inch could mean the difference between life and death for a pilot. This recognition underscored an understanding that these seemingly simple components, spring tabs, transcended ordinary mechanical parts, serving instead as potentially life-saving devices that could decisively influence the outcome of aerial battles. During the war, the highly classified nature of the spring tab technology meant that even many Allied pilots remained unaware of their true significance. Squadron intelligence officers were often instructed to describe the control systems vaguely if captured, so as to conceal the technological advantage conferred by this underestimated innovation. Despite extensive efforts by German intelligence services to gather detailed technical information about Allied aircraft capabilities, they ultimately failed to grasp the true importance of the spring tab system. This oversight meant that the Germans did not fully understand the technological edge they were up against in wartime aerial combat, allowing Allied air superiority advancements like the spring tabs to remain a secret weapon in the hands of its designers and users. In this way, a combination of technical ingenuity, secrecy, and continuous innovation exemplified the subtle yet profound ways in which strategic advantages could be built and maintained during fierce conflict. The crash investigations into malfunctioning aircraft revealed a critical problem, but unfortunately, by the time these issues were identified and understood, it was often too late to implement effective countermeasures. The repercussions of this control system disparity extended far beyond the immediate loss of aircraft. They also imposed significant resource burdens on the Luftwaffe. Instead of honing strategies rooted in technological advancements, the German forces were compelled to divert valiant efforts into developing emergency solutions, such as hydraulic boost systems, which were intended to ease pilot burden. These makeshift modifications, while providing some relief, represented an inefficient use of scarce resources, which could otherwise have been invested in producing more aircraft, training additional pilots, or enhancing existing technology with more substantial improvements. The hours of manpower dedicated to investigating and attempting to mitigate the advantages conferred by the spring tab mechanism signified a concealed toll, one exacted by the technological inferiority of their control systems. This resource drain occurred at a time when every asset held critical importance in ensuring the survival and effectiveness of the German Air Force during a time of relentless conflict. In the broader scope of military history, the significance of the spring tab system was initially underplayed, primarily because many post-war chronicles favored more conspicuous technological breakthroughs such as the jet engine, which revolutionized speed and altitude capabilities, or radar, which transformed battlefield awareness. The subtle but powerful mechanical device, the spring tab, that had in reality provided profound advantages in traditional dogfights, remained overshadowed by these flashy innovations. It took several decades of meticulous technical analysis by aviation historians to fully comprehend the pivotal role that the spring tab played during wartime. Their rigorous studies unlocked the understanding that even seemingly minor mechanical devices could induce strategic shifts of great consequence. Accounts from ground crews who serviced the aircraft have further enriched the understanding of the control system dilemma. Mechanics detailed how pilots often returned from missions physically drained by the heavy forces required to operate the controls, so taxing that some soldiers were unable to fly again for days, suffering from severe muscle fatigue. This strain was markedly less in Allied aircraft like the Tempest, which, thanks to their improved control systems, allowed pilots to undertake multiple sorties within a single day without experiencing comparable exhaustion. On the other hand, the chief mechanic Otto Bergmann, who worked on the Jagerschwader 26, observed a notable trend. Pilots increasingly clamored for modifications aimed at lightening control forces. Desperate measures ensued, including dangerous field expedients such as removing armor plating to reduce weight. Actions that, while risky, underscored the severity of the challenge faced in fighting an effectively controlled aircraft. The story of the spring tab illustrates the essential importance of incremental innovation, how persistent, continuous improvements can lead to substantial advantages over time. The control systems fitted to the Tempest, for example, were the culmination of many years of meticulous research and development, tracing their origins back to interwar days when engineers examined control system mechanics. These efforts underscored a vital lesson. Investments in seemingly mundane groundwork technology during peacetime could yield decisive wartime benefits. The evolution of the control system exemplifies how sustained focus on incremental progress, be it through better materials, refined mechanisms, or small engineering tweaks, can result in a significant edge in combat. The contrasting approaches of the Royal Aircraft Establishment and their German counterparts highlighted the importance of methodical research. The British employed a systematic, comprehensive methodology, subjecting aircraft models to extensive wind tunnel testing and theoretical analysis, uncovering viable solutions well before a crisis arose. Conversely, the German approach was more spontaneous and less structured. Their engineers often relied on intuition and ad hoc experimentation, which, while innovative, failed to produce timely solutions, often waiting until the problem became critical and repair efforts were too late. Within this context, cultural factors played a significant role. German engineers, famed for a penchant towards sophisticated, complex solutions that demonstrated their technical prowess, sometimes neglected simpler, more practical fixes that could have delivered immediate benefits. Furthermore, the focus on revolutionary technological pursuits, such as developing jet propulsion systems and rocket technology, may have distracted from recognizing the value of evolutionary improvements like the spring tabs. These innovations, while less glamorous, offered practical benefits and could have been integrated more promptly if not overshadowed by the pursuit of ever more spectacular breakthroughs. The German military and aviation industry's emphasis on crafting revolutionary advancements perhaps blinded them to opportunities for incremental enhancements, which, had they been adopted earlier, might have alleviated some of the control issues faced in combat. The overall narrative underscores a critical reality, that the path to technological superiority often lies not solely in groundbreaking innovations, but equally in steady, pragmatic improvements that build upon existing frameworks, offering reliable and immediate advantages in the chaos of wartime aviation. The adaptation of spring-tab technology across various aircraft types following the conclusion of the war vividly demonstrated its remarkable versatility and fundamental robustness. This innovative control system, initially conceived for the Hawker Tempest fighter, evolved beyond its original purpose to be incorporated into an array of aircraft, ranging from civilian airliners to military transport planes. Such widespread adoption served as compelling evidence that the concept pioneered by Hawker was not confined to the domain of high-performance fighters alone, but possessed a broad potential for application across different aviation sectors. The extensive use in aircraft like the Douglas DC-6 and other post-war airliner models underscored how innovations initially driven by military necessity could be seamlessly translated into commercial aviation improvements, thereby benefiting hundreds of thousands of passengers and civilians globally. Though the roots of the spring tab system can be traced back to the intense and desperate aerial confrontations of the years 1444 and 1445, these origins were seldom openly acknowledged in post-war discussions. During the final months of the conflict, the German military intensified their efforts to counter the increasingly dominant Allied air forces, employing tactics that reflected a deep sense of urgency and desperation. For instance, they issued orders directing their fighters to refrain from engaging unless they held a clear advantage in numbers or had gained a significant altitude advantage, tactics that aimed to maximize their limited resources but often compromised their operational effectiveness. Such tactical restrictions, combined with the technological superiority of Allied aircraft equipped with the spring tab system, most notably the Tempest, significantly curtailed the Luftwaffe's ability to mount effective opposition. These measures ultimately contributed to the clear dominance of Allied air power in the skies over Europe. One particularly tragic aspect of this period involved the infamous Ramjer units, German service units trained to undertake suicide ramming attacks against Allied bombers, an extreme response born out of the inability to conduct traditional interception missions amid the overwhelming control of aircraft like the Tempest. The formidable high-speed maneuverability and precise control granted by the spring tab system meant that even poorly trained teams, often involving very young German pilots with fewer than 50 hours of flight experience, would be sent into combat with little chance of success against these technologically advanced fighters. Their human story exemplifies the many tragedies of the final war years. Young, inexperienced men confronting an enemy master of the skies, armed with technology they could scarcely comprehend or counter. These inexperienced pilots faced not merely superior enemies, but aircraft equipped with fundamental technological advantages, most notably the spring tab system itself, which granted fighters unmatched maneuverability at high speeds. Training schools attempted to prepare new pilots for the inevitable control challenges they would encounter in combat, emphasizing familiarization with the peculiar behaviors of spring tab-equipped fighters. However, despite rigorous instruction, there existed a physical limit, an almost insurmountable obstacle, that made effective maneuvering at the very high speeds these aircraft could achieve an impossible goal. The design of the spring tab system ensured that during high-velocity flight, Pilots could not override the aircraft's inherent control limitations, thus preserving full control authority only within certain operational speed parameters. The meticulous preservation and examination of wartime documents concerning spring-tab technology offer invaluable insights into the innovation processes that occurred under extreme pressure. These records reveal a systematic approach undertaken by British engineers who creatively and methodically addressed and resolved complex technical challenges, all while maintaining tight schedules of production and fulfilling urgent military demands. Correspondence between Hawker's design office and Royal Air Force operational squadrons underscores the iterative nature of this advancement. Knowledge gained from real combat experience continuously informing subsequent refinements. These rapid feedback loops exemplify a process of continuous improvement that was far more responsive and adaptive than similar developments conducted by German aircraft manufacturers, who often found themselves cut off from frontline units by the breakdown of communication channels and diluted command structures. The crucial role played by test pilots in the evolution of the spring-tab system warrants special recognition. Men such as Bill Humble and Philip Lucas committed themselves to exploring the limits of the flight envelope in dangerous, high-risk testing flights. Their efforts involved fine-tuning the spring rates and tab configurations, pushing the aircraft to its extremes to discover optimal parameters. The dedicated and systematic data collection by these pilots provided the foundation for the aircraft's refined control characteristics, data that would later help save countless lives during combat. Their meticulous reports and test records, carefully archived, illustrate a scientific and highly disciplined approach to solving control problems, testing dozens of different configurations before arriving at the ultimately successful design that conferred such decisive advantages upon the Tempest fighters in combat. Following the war, spring-tab technology was not confined to Britain alone. It saw a rapid international spread, with former wartime adversaries and allies alike adopting and adapting the system for their own aircraft. This proliferation of the technology underscored its significance as a major technological breakthrough, one that bridged military innovation and commercial aviation. Its influence extended well beyond the immediate post-war years, marking a substantial step forward in aircraft control systems and exemplifying how wartime ingenuity can shape the future trajectory of civil aviation for decades to come. During the intense and often brutal conflict of the Second World War, scenarios evolved where former enemies found themselves unexpectedly becoming allies, engaging in the sharing of crucial military information and technological insights. This remarkable shift demonstrated how advancements in military technology, once considered the exclusive domain of national interest, could transcend borders. Notably, German engineers, despite their earlier struggles to fully grasp the intricacies of spring-tab mechanisms during the war, later played a significant role in refining and optimizing these systems for civilian use. Their collaborative efforts with allies underscored a profound truth. In periods of peace, adversaries could unite in the pursuit of technological progress, leading to thriving advancements in aviation technology that benefited the entire world. In the realm of aerial combat, rigorous statistical analyses of battle records vividly illustrated the undeniable advantages conferred by the spring-tab technology on the Allied side. Data extracted from combat engagements overwhelmingly confirmed that aircraft equipped with spring tabs, particularly the Tempest fighters, routinely maintained superior exchange ratios against their German counterparts. Even when placed at a numerical disadvantage, sometimes by a significant margin, the Tempest consistently inflicted more damage than they sustained. This was especially true during high-velocity dogfights, where the disparity in control system responsiveness became most evident and decisive. These statistics supported the broader strategic narrative. Technological superiority, especially in control systems, could offset numerical superiority, a principle that challenged traditional notions of aerial combat, grounded solely in numbers. Fundamentally, the mathematics that traditionally dictated aerial battles favored large numbers, hinging on the assumption that more aircraft would always translate to higher success rates. However, this notion was fundamentally challenged by the technological edge provided by innovations like spring tabs. A solitary Tempest could confront and often effectively hold its own against multiple German fighters, aircraft that, due to their more primitive control systems, were hampered in executing complex maneuvering at combat speeds. The engineering behind spring tab construction, particularly the specialized alloys and resilient springs, played an essential role in enabling such performance. These springs had to maintain highly consistent properties over a vast expanse of temperatures and endure millions of compression cycles without failure, exemplifying a peak of British industrial capability. Producing these high-performance springs proved increasingly challenging for Germany as the war progressed. The nation faced critical difficulties in sourcing the raw materials necessary for manufacturing the specialized steel alloys essential for reliable spring construction. Additionally, the extensive damage inflicted upon German factories and the disruption of raw material supply chains significantly hindered their to produce the consistent high-quality components needed for spring tabs. Consequently, this scarcity and manufacturing strain compounded their technological disadvantages, further impairing their fighters' maneuverability and responsiveness. The influence of spring tab technology extended far beyond simple mechanical improvements, profoundly affecting pilot mindset and tactical doctrine. Aware of the Tempest's superior high-speed agility, largely enabled by the effective control offered through spring tabs, German pilots were compelled to avoid certain categories of combat maneuvers altogether. This strategic constraint forced them into less advantageous, often disadvantageous turning battles. Fights in which the Germans were more vulnerable due to their aircraft's inferior speed and agility, compounded by limited fuel reserves. These tactical disadvantages shifted the initiative decisively toward Allied forces, who exploited the enemy's hesitations and the staging area restrictions resulting from the Germans' altered combat philosophy. The inability of German fighters to execute their preferred high-speed slashing tactics, once a mainstay of Luftwaffe strategy, effectively neutralized a critical edge in combat. No longer able to rely on rapid, sweeping attacks from above or below, German pilots found themselves often engaging in dogfights characterized by tight turning circles, a situation that favored aircraft with superior agility and control. For the Germans, this transition meant facing a more disadvantageous battleground where numerical inferiority and dwindling fuel supplies could prove decisive factors in combat outcomes. All these effects were vividly documented in technical manuals and military training documents, where an array of charts and diagrams conveyed the complex engineering principles behind spring tab systems. Such materials also emphasized how to present this highly technical information clearly enough for pilots and ground crews, regardless of their varied educational backgrounds, to understand and effectively operate these advanced control systems. The engineering communication strategies employed, ranging from simplified explanations to detailed diagrams, reached a remarkable level of pedagogical sophistication. This enabled personnel with diverse levels of technical expertise to grasp the core concepts behind spring tab operation and utility swiftly. The success of this approach was pivotal in ensuring that the fighting forces could fully exploit the technological benefits without being bogged down by overly complicated technicalities. An appraisal of alternative methods explored during the war, aimed at reducing control forces or improving maneuverability, underscores why the spring tab concept emerged as the optimal solution. Among the various systems trialed, ranging from aerodynamic balance tabs to other innovative control modifications, the spring tab design scored high on its overall effectiveness, ease of production, reliability, and straightforward integration into existing aircraft structures. Its balanced combination of these qualities explained why the spring tab was able to outperform and outlast other experimental technologies, solidifying its vital role during the conflict. In summary, an in-depth examination of the modifications involving the deployment of split rudder volume, RVO tabs to assist hydraulic boosting, revealed that although numerous alternative solutions existed theoretically, only the spring tab design encompassed all the critical traits necessary for successful and reliable operation during wartime conditions. Extensive recovery and forensic analysis of crashed aircraft subsequently provided compelling evidence, indicating that German technical intelligence services had become aware of the existence of spring tabs by the latter part of the year 1944. Despite this awareness, these agencies failed to comprehend the full significance and potential strategic advantage offered by these devices, or to develop effective countermeasures swiftly enough to influence the ultimate outcome of the conflict. Furthermore, intelligence reports describing these devices often depicted them merely as modified trim tabs, a description that reflected a fundamental misunderstanding of their true functional role and strategic importance. Such misinterpretations pointed to a significant failure in technical analysis, a misjudgment that ultimately proved costly for the Luftwaffe in the final months of the war. This lack of accurate technical comprehension led to missed opportunities and delayed responses, which could have altered the air warfare landscape had the intelligence been better, more precise, and promptly acted upon.